And our next talk will be on Radical S, an active radiation shield flying on the Swedish Space Corporation Sub-Orbital Express.
Thank you very much to the hosts and to the conference organisers for this opportunity to speak this afternoon. So I'll start by informing you about the opportunity. So the Swedish Space Corporation launch from Kiruna up in the Arctic Circle of the Northern Hemisphere, and we have an experiment manifest on Sub-Orbital Express 3 or MESA 15, which has faced a couple of delays, but is now scheduled to fly in November this year. The MESA is one of the kind of middle-sized rockets that Sweden offers, and it'll be going to an altitude of about 250 kilometers. Now, the flight is reasonably short. It's around about 12 minutes, 12 to 15 minutes long, and with just 6 to 7 minutes of microgravity, which we won't actually be making use of with this flight. In fact, the key thing for us is the radiation environment up there in the with the landmass very close to the magnetic pole in the north. We're going to be able to expose our payload to a very high radiation dose at a reasonably low altitude, and we're in Australia, so we don't have the same landmass next to the or an easily accessible magnetic pole in the south. Now, we've been developing the payload for quite some time, and we're just entering the kind of exciting stage between development and testing and gearing up for the launch, but I'll give a more detailed timeline a bit later in the talk. So the key thing here is that we are developing an active radiation shield. So rather than just using passive materials that represent a simple barrier between radiation and crew or electronics, we're making use of magnetic interactions to add extra protection. In terms of testing, we do have some space radiation analogues in Australia. We've got a neutron source, some protons and heavy ions, but they're not the same energies as would be encountered in space. The active radiation shielding principle operates off the Lorentz equation. So a particle will experience a force when it encounters an electric and magnetic field, and will, depending on the velocity that the particle has, it will deflect by a certain amount. Now, NASA and ESA have, of course, invested huge amounts of money in researching active shields, but most designs are huge toroids, usually cryogenically cooled, and the goal has been to protect large volumes of the spacecraft permanently. And our project adopted a completely different approach from the get-go, on the assumption that launching these huge, massive things that require a lot of operating materials and costs are not fit for launch and not fit for long-term operation. So the constraints that we applied to our project were, first of all, it has to be lightweight to reduce the launch costs. It can only operate off existing spacecraft power. So if we assume ISS is operating off 160 volts, then that's all we have. And magnetic fields of the three types of active shielding are probably the easiest to generate and easiest to control. With the opportunity that we have with Sweden, we also have to ensure that the payload fits within a 1U volume, so we have to scale it down massively, and the shield must be able to operate autonomously. So these are quite the number of constraints for the payload and for such a solution. The 1U design consists of an aluminium bus with a minimal frame that simply can handle the Gs at launch, about 20 to 25 Gs on the rocket. It consists of a shield with a novel design, an instrument suite. It takes its power from the rocket, so it doesn't need its own power supply, and simply has a 21-pin plug to connect to the rocket. So the key point about the shield here is that instead of having the toroid generate the magnetic field through the center of the spacecraft, which would be damaging to the humans on board, this design puts the magnetic coils and the magnetic field in the walls, leaving a void volume inside the spacecraft, so the crew are unaffected by the magnetic field. This is the miniaturized shield concept, and the active components comprise of polyethylene slabs with copper coils wound around. For this particular prototype, we have 8 segments, so 8 slabs of polyethylene, and each slab has approximately 92 windings. Simulations of the most simple shield with just the 90 windings and a 5 amp current generate some modest field strengths. So 6 millitesla modeled in the center and 2 millitesla at the ends. In terms of contamination to other payloads that are nearby, the B field strength reduces to 0 at 5 centimeters from the shield when it's at 5 amps and generating this amount of magnetic field. The instrument suite is very simple and very basic. We don't have any room, so we have a Geiger counter, a magnetometer, and a GNSS. It turns out the GNSS is unlikely to be able to track to provide reliable data, particularly in the hypergravity phases of the flight, because the rocket will simply be moving too quickly. But the rocket has its own GNSS data, so we can match that up with the timestamps of the magnetometer and Geiger counter data. I have a group of students who are working on the electronics and making it all tidy and fit inside the 1U volume. And the operation sequence over the 12 to 15 minutes will be that the payload will be on the launch pad in the rocket, instruments will turn on, and they will start saving data. The shield will be off, then the shield takes its active signal from liftoff, and the shield will stay on for 15 seconds and then be off for 15 seconds. And as it's on and off, data will be being saved continuously on an SD card, and there'll be no downlink, so we'll get the data when the thing comes back down.
1 minute.
Thank you. The basic design has been published in a conference proceedings at the end of last year. The Geiger counter has 2 count modes, fast and normal. It can't make any distinction between particles, although it will only be measuring charged particles. So we're hoping, the majority of the signal is going to be protons. The electrons probably won't contribute too much. So we're going to be able to make a reasonable assumption that the counts are protons, and we should be seeing a reduction in that count when the shield is on. Magnetometer, this data doesn't make any sense because it's been taken in one spot, but we can match that up with altitude. GNSS doesn't work. In terms of our timeline, the next exciting thing is taking the payload to ANSTO, the Center for Accelerator Science, that has a 20 mega electron volt proton beam. This will be the first kind of real test of the shield. And then in August, we'll be shipping the payload to Sweden. The payload is part of a rideshare module that Sweden are offering, and this is a cost-effective way of launching small payloads for a reasonable cost. I'd like to acknowledge my group, my students and colleagues, and the Swedish Space Corporation for this opportunity, and RMIT for funding the launch. And thank you all very much for your attention.
Thank you. That's very exciting. So there are a couple of questions that came in real quick. How does this scale in terms of power requirements and mass for crew protection, assuming a cylindrical shape with radii greater than 3 meters?
Yep, great question. So what scales, the polyethylene is the thing that will scale. So if we say we have a 50 centimeter slab of polyethylene, excuse me, that will then be, it will perhaps have, say, 3 iron cores drilled in kind of equally spaced within it, and they will have cores wrapped around them, and they'll be generating the field. So the distance between coils will be the thing that expands when it's scaled up.
Okay. And one more question. Let's see. Oops. What is the cutoff energy rigidity?
Of particle energies that can be deflected.
Yep.
It all depends on the strength of the B field. And so if we go 6 millitesla won't do very much. 6 millitesla will probably deflect 100 kiloelectron volt particles. So the challenge is to increase the magnetic field without drawing too much current, because there's also a lot of heat issues with drawing more current. So in fact, what we report in the conference paper is that maintaining that limit of the 160 volts coming from the spacecraft, what we can actually do is we can obtain a current in a short pulse of perhaps up to 150 amps for a very short period of time and generate a large B field. So if we had advance warning perhaps of a coronal mass ejection, what we could do is we could alert the crew, have them go into one particular module that has the technology, activate this very high current, and generate a pulsed magnetic field. So it won't stay on permanently, but what it will do is just for a few, say, over a period of hours, we can reduce the dose a little. So when this isn't a permanent solution, it's not going to be on all the time, but it would be active enough that it could protect them for a little bit longer.
Wow, okay. That's really interesting. Thank you very much. And you do have one more question in the chat, but we have to move to the next speaker. So if you can respond there, that would be great. Thank you very
Sure.
much.
Thank you.